For today's webinar. As mentioned, today's webinar features work done by several researchers at the University of Utrecht, Dr. Cedric, Thieulot, and Glerum, Menno, Fraters, and Vince Backerman. Today's webinar recorded and will be available for on-demand viewing through geodynamics.org. During the webinar, only the host and presenter will have their microphones enabled, so use the chat window to type in your questions or to communicate with others. Presentations in this series will be approximately 50 minutes in length, with questions and answers following during the remaining time. Today's talk continues our series on benchmarking and includes some exciting science using the SIG and community developed code aspect. Today's talk will be given by Cedric Thieulot and Menno Fraters. Cedric received his Ph.D. from the University of Groningen in the Netherlands. He has a broad range of interest, from developing compositions for string instruments to developing codes involving thermo-mechanically coupled Stokes solvers. He is the author of the finite element code Elephant and Phantom 2D, which has been used to study a wide range of problems in lithospheric deformation, including rifting and orogenesis. Today, he and Menno presents his work initiated at last year's Aspect Hackathon on benchmarking and an application of the code to problems in subduction zone modeling. In their talk, Aspect from Benchmarking to 3D Subduction Applications. So take it away, Cedric.
All right, thanks, Lauren, for the kind words and nice introduction. Yeah, thanks all for joining in. So yeah, this is a joint effort between the three of us and our fearless leader, Wim Spakman. So he's the head of the lab. So today we're gonna split this this presentation into 4 parts. The first one is running aspect on the Dutch supercomputer Cartesius. The second part is about visco-plastic thermal convection, so it's a benchmark. The third part is about Aegean subduction, and that's the work of Glerum. And the fourth one will be presented by Menno here next to me. So let's dive in. Meet Cartesius. That's our Dutch supercomputer. It's not in Utrecht. It's actually in Amsterdam, and it's been recently upgraded. So as you can tell, it's not the best in the world, but we have quite a few cores now, and they have showing you this piece of art, which is Cartesius. So you have the specs of the supercomputer there. And so we have our own little cluster here in Utrecht, and it has 1,000 cores, but it's 4 or 5 years old, so it's getting a bit outdated. And Anne has been got a pilot study to actually log on Cartesius and run Aspect there. So page 4. So the idea of the pilot study is to carry out scaling tests, because basically they will not give you a lot of CPU hours unless you show that the code you want to use is appropriate and can actually take advantage of the architecture. So they give you, I think it was 100,000 core hours, something like that. And the idea is that you carry out scaling tests, and with their help, you identify and, if possibly, fix potential bottlenecks. And fortunately, we have Thomas Geenen, who works for Surf-Sara. And Surf-Sara, they are actually the company or the institute, if you want, running the supercomputer. And the reason why we're very happy is that Thomas did his PhD with the very first version of Aspect. So he knows Aspect rather well, and he is quite helpful in helping us setting up Aspect on this supercomputer and fine-tuning it, if you want. And so the idea is that, yes, if we get good scaling results, then we can ask for more, like a lot of more CPU hours for big production runs. Okay, next page. And we could, of course, do tests on the Stokes sphere in 2D and 3D, but it's not that much fun, actually. So we have decided to do it on a rather realistic test case, which is it's a paper I'm preparing. It's a benchmark paper, and it's based on it's a very simple 3D slab detachment case. So you have a layer of sticky air. Underneath the red layer is actually a lithospheric layer, which is described by a power law viscosity. And then underneath the blue, the light blue, is actually the mantle described by a power law of different exponents. And Anno is using this as a test case because it contains most of the ingredients that we need for our production runs, which is high viscosity contrasts, very nonlinear rheologies, potentially temperature in the future. So she's been running this setup and fine-tuning it on Cartesius. And as you see in the lower right corner, there is this EGU logo. Well, it's because her results and mine and results from other people will be presented at EGU in about a month's time. Next slide. We had a bit of delay, but there were actually a few. Anna was able to actually carry out a few preliminary strong scaling tests on that particular setup. As you can tell, it was about 3 million degrees of freedom, so not as big as we wanted, but that was once again preliminary, and it looked rather well. Like she's run cases up to 256 cores. And she was looking at the different pinnings, you know, how many cores per node you use and that sort of thing. So either you use 16 out of the 24 or 24 out of the 24. And it makes a bit of a difference. But unfortunately, well, the system was too small to actually really, so that we can really take advantage of more cores. So we've encountered quite a few problems. So if you switch to the next page, so the little Garfield here on the status means that, well, Anna got a bit stuck there because Cartesius has just been updated and upgraded, actually, and they have two versions of IMPI. So one is IMPI from Intel, and the other one is the XMPI library from the supercomputer itself. It's a Bull supercomputer, and both of them gave different kinds of problems, which is what I write underneath, which is either something to do with the restart or the visualization, as in files were not produced. The visualization files were not produced. And so she's been sorting this problem out with, once again, thanks to with Thomas. And as of pretty much yesterday or this morning, it seems to be all fixed and all ready. And they're going to move on with XMPI. So, sorry, with IMPI. I underlined the wrong one. So yeah, so basically now she's got about a month to finish all the scaling tests. So hopefully by the hackathon, we'll have, well, the strong scaling and hopefully the weak scaling tests as well to show you guys. So that was for one part that took quite a lot of time, actually, unfortunately, but this is how things go. We were rather successful with the next endeavor, which is page, following page. The visco-plastic benchmark. So actually, we went to a GeoMod, which is well, a geodynamics conference in Europe every other year. We're there at GFZ in Potsdam last summer, and we met a few people, and they told us, "Hey, you guys should join in because we have this community benchmark that we're running." And as you can tell, there's quite a few people on this effort. Most of them based in Europe, and so we dived in like very fast. From September on, we've been working on this, and the paper was submitted well 2 weeks ago. And so I'm just going to take you through this. It's a rather simple setup. So if you go to the next page. For some of you who are familiar with Aspect, you know about the Blankenbach test. It's basically a Blankenbach type of setup with a nonlinear rheology, like a visco-plastic nonlinear rheology. So it's a unit square. Temperature is 1 at the bottom, 0 at the top. You introduce in the center here an initial temperature field, which has a slight cosine sine perturbance with a small amplitude. And if you look on the left, it's solved for incompressible flow, pure Boussinesque, and the viscosity is given by this harmonic averaging of a temperature part and a plastic part. The temperature part is something called the Franck-Kamenetsky approximation. So it depends on temperature and depth, which is a proxy for pressure, basically. And the plastic part is some kind of Bingham fluid, so if you want. So you have an eta star parameter and then your yield value sigma y. So next slide. How am I doing? Of course, we had to run. Yeah, we had to run quite a few of these models, and we had to agree on some measurements. So fortunately, most of them were already implemented in Aspect, such as the average temperature, the Nusselt number, the VRMS. I believe Anna and Menno worked on the viscous dissipation and the work measurements. You have on the right the list of codes that participated. They're not all very famous. We had a nice blend of finite volume, also finite difference and aspect, so finite elements. So also my code elephant. There was fluidity also for finite elements and Phoenix, so kind of big codes there. And you have Steig YY, which is the flagship code of Paul Tackley, and some other codes, and Yak as well, which is gaining momentum. Next slide. And of course, as in every study like that, you have different cases. So you go from rather simple to more and more complex. We had basically 5 cases, and the idea was to start with, as you can tell on the first line of the table here, sigma y was null, eta star was null. So basically, it was only a thermally driven, if you want, system. There was no plasticity in there, only thermal dependency. So it gave rise to a stagnant lid, and then you see different types of convection types, so mobile lid or periodic. I'm just going to come back to that. Just to give you a little flavor, so the case 1, and I recall here, okay, so, next page. You see here at the top that basically the eta plastic is gone, so there is no plasticity, and the linear, what they call the linear viscosity, also does not contain any depth dependency. This gives rise to a stagnant lid, and what we've been doing is look actually at, for instance, the RMS velocity of the system as a function of the number of, well, let's call them elements or cell in one direction. So basically going from 8 to 512 squared. Aspect is the green star, which starts rather high, and then very fast at 64 squared resolution gets right in the middle of the pack, and then nicely converges to the values that the others got. And they delineated actually the finite volume codes from the finite element codes. I'm not sure what really we see there, but this is just one of the many plots, and Aspect always falls right in the middle. So we're pretty happy and without much of a trouble. Okay, next slide, please. And then if you look at what the actual plots, you have the RMS velocity on the left corner, the temperature on the right, and the viscosity on the bottom right. And so it actually converges to a steady state there, so it doesn't change over time. And these are the plots that are included in the publication. Next slide. What was a bit more interesting actually is in the case where you get this, if you look at the right column, I have put here this mobile and then periodic and then stagnant yellow stickers. The idea was to actually change the yield stress, so this sigma y. And what happens is that when sigma y is around 3, you get a mobile lid, then somewhere between 3.8 and 4.5, let's say it's periodic, and this is what is plotted on the left part. Here you see these nice oscillations with a very clear-cut frequency. And then if the yield stress gets higher than 4.5, then it goes back to being a stagnant type of convection. So you see the results of aspect on the bottom right corner, and it falls. I didn't have the space here to plot all the other codes, but we fall right in the middle of the pack as well, and remarkably well actually on that one. So once again, very happy, and nothing much to discuss there in terms that it worked nicely. So this is submitted, hopefully, who knows, accepted by the hackathon. That would be nice. And then we'll be able to share the input files with you guys, to put them in the code as tests, for instance. The third part I wanted to show you guys today is actually the work of Anna, or her PhD topic, actually, is the Aegean Subduction. So this is the Mediterranean area, which in terms of structural geology is an absolute mess, as you can tell. A lot of slabs and faults and all kinds of curved areas, and it's still a matter of debate. There's a lot of work on every single piece of slab in this area. What Anna is going to focus on, if you go to the next slide, and you should see here this dashed rectangle, is this particular area, which pretty much englobes Turkey, Greece, and North Africa. And if you go one slide further, I've delineated there actually three major structures. So the top curved one is actually the North Anatolian Fault. The bottom wiggly one, if you want, this is the subduction trench. So you have a slab underneath dipping towards the north. And then we have this kind of, let's call that quarter of a circle type of structure, which is a system of faults there. And so this is her domain of study. It's been carefully chosen for many reasons, so I won't go into that. And if you go to the next slide, you'll see a beautiful error, which, okay, never mind. That was just a 3D rendering of that plot. It's a bit of pity, never mind. Moving on to the purple and yellowish slide. So the idea is that last year we had a rather brilliant master's student called Casper Pranger, who was a bit of a wizard in Mathematica and developed for his own master thesis, which was called Numerical Modeling of Instantaneous Subduction Dynamics of the Banda Arc Region. So you see actually his mesh there. So in Mathematica, he based himself on mental tomography and all kinds of geometrical constraints, and was able to actually build a tetrahedral mesh that was fitting nicely all these complex geometries. And on the right, you have an example of like an excerpt, if you want, of the oceanic crust, the wedge, and the slab, and the light pink is the mantle. So we have that, if you want, at our disposal, and the idea is how can we use this tool to actually interface with aspects. And this is at the moment sort of the tentative workflow we have, which is the next slide. So on the left, I write here structural geology and mental tomography. So these are pretty much the inputs we have, sort of the data, if you want. We have the meshing tool of Casper, and this will actually, Casper provides us, if you want, with triangulated interfaces between domains. So basically, it gives us point coordinates and their connectivity. So each interface between domains is actually triangulated with a certain ordering, which allows us to actually know whether we are in or out of a given surface, or outside, inside. And Anna wrote a big plugin, which is still under construction, which is this red dashed rectangle there. So basically, at the moment, Aspect is reading an ASCII file, and at startup is computing a composition value for every single node. and based on that, the simulation can start. Her latest work actually now consists of also using this geometrical information to set the temperature in the slab, because this is also it's not that trivial actually, and this is in progress. Next slide. Just to give you a flavor, you should see actually this 3D box. So it's a proof of concept at the moment. So I here point at the 3D slab. The pink points are the points that come from the triangulation of our student. And Anna is using this to actually sort of compute this composition and then also adapt the grid, as you can see on at the interface between the slab and the grid. And well, it works nicely. And if you look at the next slide, sorry, she's so far as to actually be able to delineate now the crusts, the lithosphere, and the slab. It's still very tentative. I mean, the thicknesses are wrong if you want, but that gives you a flavor of where she's going. So each of these layers, if you want, is at least one composition, and we'll refine that in the future probably. And so this is actually her work at the moment. She's busy doing, making sure that she gets the first, basically the setup right. And she'll be showing these plots and hopefully many more and some early calculations at the EGU. So that's pretty much up for me. I give now the chair to Menno, who's going to talk about his work. So I'll just share his document. Right.
Okay, well, thanks. Let's see how this works. Where's my mouse?
Just scroll down. Yeah.
Oh, it works.
Oh, now it works.
That's really nice.
Okay.
Because I have a lot of slides together, but so I'm Menno Fraters, and I'm going to talk about my project basically, which is well, let's this better, which is going from kinematics to dynamics in the Caribbean region. But I first want to do a little bit of a recap on my master thesis. This is something I presented at the last hackathon, which is to the thermo-mechanically subduction models, and well, making the initial compositions for them, and building topography through the use of sticky air, which is basically a very low viscosity layer on top of my model. And you can see that, well, there's some topography building, and the results are, for example, what you see here is slab detachment. So what I've then been working on is, I'm now working on, is the Caribbean region. And that's something that's a very complex region, which is still poorly understood. And that's because the kinematics are contested. And the different kinematic models predict different, well, for example, geohazard. Just an example is that some kinematic models predict under the sea of the Caribbean a large fault, while others don't. And if that fault is present, then well, and erupts, then there might be a large tsunami in places where no one have ever predicted them or protected against them. But also in georesources, we need to be able to predict where we can find those things. For the paleoclimate, when did, for example, the sea close there? When was there still connection between those two seas? So to predict, it's crucial to understand the dynamics, and to understand the dynamics, it's crucial to know its history, its kinematic history, to be more precise. And so what I'm going to do in my first part of my PhD project is, well, getting the best kinematic model. The problem is there are several, as I said before, and they are completely different in what they say what happened. That also brings, well, a solution, which is I will try to model them with aspect and see if I can compare them with the tomography. So that's the first part of my research. So what do I need for my models? Well, quite a big list. First of all, rheology. That's some phase changes might be very important. Spherical mesh, because we're looking at a very large area, so we will need to be able to account for the curvature of the Earth. Good adaptive mesh, I will explain a little bit about that later on. Stress boundary conditions, free surface, good initial conditions, and we want it fast, of course. So first of all, the realistic rheology. That's something Anna has been working on quite a bit and well, quite successfully. So we have now a plugin which enables us to use dislocation creep and diffusion creep, and also a more Coulomb plasticity. The phase changes, well, are of course an aspect, but still need to be added to that the plugin. So what I've been working on first when I started the PhD was basically an extension of what I did during my master thesis, was looking at how can we control the AMR, the adaptive mesh environment, in combination with the plasticity. And what you see here in the first two pictures is, well, a lithosphere with a sticky air on top. That's the blue thing on top. And you have some topography building going on. But what's more important is that what you see is that you're looking at, by the way, you're looking at viscosity patterns from 10 to the 24th is red, and 10 to the 19th is blue. I forgot to put a scale on there. I'm sorry for that. And what you see is that there's a very chaotic pattern. And when you look at the mesh, and also if you look at it over time, it's changing a lot. It's not constant, and that's something which is very important for plasticity. As you can see in the two figures below, you can see that if we use a constant grid size, that's the shear bands, which you see on the left side, are very well developed up till the place where my mesh gets coarser again. So, but we can't really do this for our model because it takes a huge amount of calculation power and time, and it's not really adaptive. Because if my slab is subducting, then it doesn't move with it, because it has just been done well in this area. Use a very high criterion for the environment. So the solution we came up with is basically with a new system within aspects where you can remove flags and add flags for the coarsening and refinement. What we do there is base it on isotherms. So for a low temperature, we say, well, between this temperature and this temperature, I want this maximum refinement and this minimum refinement, and between this and this temperature, etc. Other thing I did, because of the sticky air, we don't need a lot of resolution there, so I added to the plugin some line that I can exclude one composition, which in this case is sticky air, and you can see it works very nicely. It will always follow the slab, whatever it does. You can see it makes a really strange shape here. It will follow it, and even it also works with the true free surface implemented by Ian Rose. As you can see in this figure, it really nicely follows the thing I'm interested in, and it keeps a good resolution there, so plasticity can develop fairly nicely. And that is all done well with a few lines of code. You can, or in the input file, just a few lines where I define the isotherms. You can set, well, the relative things like max and min. As you see in the first two columns, or you can say, well, I want refinement level 4 and 5. So that problem was then solved. So I went on to the, well, no, that's later. Something else I want to talk about is stress boundary conditions. That's something which we will also really need, and the question is, of course, why would we need those? Well, first of all, stress boundary conditions will have more realistic flow than closed boundary conditions, as you can see in the paper of Cedric et al. 2012 in Solid Earth. And there are also, stress boundary conditions are also a more realistic way to push plates, because of velocity, well, it can, in theory, end in infinite stress, but stress, yeah, it more simulates what the Earth's actually probably doing. And another thing is that you can save a lot of computational time by making the domain smaller without changing the problem. That's actually the case with open boundary conditions, which is a form of stress boundary conditions where you prescribe the lithostatic pressure on the sides. And last but not least, it's actually easier to set up the in and outflow for very complex geometries, because you can just prescribe some inflow somewhere and then prescribe, well, I have open boundary conditions for the rest of the model, and then the inflow and outflow will compensate themselves really nicely. So that's something, let's go back. Well, that's something we actually want to, oh, wait. 1 second. So that's something we want to do during the hackathon. That's something which is on our list. And well, let's go on with something I've been working on the last month, basically, is how to distribute materials and temperature in complex spherical geometries. So what we need is flexible methods for compositions, temperature, in spherical model, and for complex 3D regions, as the Caribbean region is, and allow for topography build-up. So what we want to look at, or what I want to look at, is the Caribbean region, and one of the theories behind it is that it started out something like this 200 million years ago. Just to say, this is just used as an inspiration to build the proof of concept, which I will show you now. On the left side, we had a large old ocean, the Pantalessa Ocean. You see North America, South America, a fault in between them, and the Caribbean lithosphere. And we're going to look at the red, the part in the red square. So I already told you where, about 6 objects we need: the Pantalessa Ocean, North America, South America, Caribbean lithosphere, the fault, and a subduction zone. And I wanted to parameterize that in a certain way, which you can see in the next slide. So what you see here is what you would see in the input file as a user. You define certain objects, you prescribe a temperature model to that, a composition model. You say where it is, so you use coordinates, and then you can parameterize it even further by saying, for example, my continent G is 115 kilometers thick, or my ocean uses a plate model, and the plate model uses the parameters that it's 95 kilometers thick. It has a ridge at a certain location, the plate velocity, etc. And using these kinds of methods, I've been able to construct, a proof of concept of this setting, which you will be able to see in the next slides. This is a top view. So if we go 2 slides back, this in the red part is what you see here. You have your Caribbean Ocean, the old oceanic plate, North America, South America, a fault and a subduction zone. And well, I must mention the third mesh has been made with the help of Sarah Stamps and Wolfgang Bengert. So many thanks for their help. And now we're going to switch. So we're going to look in 3D, which looks a bit like this. We're now looking from the northeast, and we're looking from basically America, the North and South America, and the fault. We're looking towards the old ocean and the Caribbean plate. And as you can see, you have your subduction zone in there. And now we're going to go down, I think. Yes. So we move from this, move down, and we're looking from below now. And well, you see your continental plate again. You see in the background, you see how the new Caribbean plate is situated in the old ocean, old Pantalessa Ocean. And now we're going to go up again and go to look from the north side here, go back and forth, and you basically see the same setting as before. We have our old ocean and the continent and the subduction zone. So that's something which I finished a few days before this, and it seems to be working really nicely at the moment. So what is also an added bonus, because what I used is still the same isocontour plugin, which I showed before, and it's still it also works in 3D where it follows where I want the resolution really high. It follows it really nicely. So when I put really complex rheology models in there, it will follow it. So just to sum it up, rheology, well, it's already done. Phase changes. Ooh, no. That's a shame. Let's see if they're all bad. Yes, they're all bad. That's a shame. Well, then I would just talk you through. Phase changes are still to be added. The circle mesh has still some problems, but those will hopefully be solved soon. We have quite a good control of the AMR currently. Such bound conditions is something which is not yet present, and we would really need for our projects here. Topography building. Well, I showed you some figures of that. We already have simple initial conditions, complex initial conditions. Well, we have a start of it, but we're still needs quite a bit of work to make it actually work really well, especially for spherical conditions. And the requirement of fast, well, that's something Anna is working on now. And well, there was a question mark there. We will see how fast we can get it. And as a last thing, I will have a talk on ETU about this, about these subjects. I talked to you also now about. So maybe hope to see you there. That's it. Any questions?
Thank you, Menno and Cedric. Quite a wide variety of topics being presented, and a lot of really exciting science. Questions. If you would like your microphone open, please raise your hand. If you'd like to type in the chat box, please go ahead and type in your chat box. While Katrina is typing in her question, I want to say that our next webinar will continue the series on benchmarking with a slightly different spin on modeling and benchmarking. The webinar on April 9th will feature Professor Lucy Flesch from Purdue University And she'll be talking about workflows and 3D geodynamic simulations of the India-Eurasia collision zone and some of the work she's done modeling that collision zone in comparisons with some sandbox experiments.
Well, I don't have a poster, but Anna will have a poster on her stuff.
I think, Menno, you have a talk, don't you?
Yeah, I have a talk. Cedric has a Pico.
Yeah, they have this new thing at the EGU where you don't have a post. It's not a talk, it's not a poster. It's basically you get a giant screen for 20 minutes, and then people will come to see you. But instead of having a poster behind you, you have a big screen where you can show movies and animations. So it's kind of halfway in between. So, and we've been careful enough to submit our abstracts in 3 different sessions for maximum coverage and exposure. Hi, Juliana.
So what formulation? The phase 3. Okay, well, as I believe there are currently two types of phase decisions in there. Something Thomas Gene put in there, and something you, Juliana, I think, have been working with. And I haven't dived into there deep enough to actually know what's the better option to use. So that's something I'm planning to think about after I finish the complex initial conditions. I don't know if you have opinions on.
No, I guess the idea is first to get the basic setup running, and then we'll fine tune in the light of, it probably will take us another few months before we get something, well, decent enough. And then, of course, we'll start refining. I mean, we'll have to equilibrate the model somehow to get plausible topographies, plausible boundary conditions. And then at some point, yeah, we will look more closely at phase change. Yeah, no,
Dat je zei dat het moest toevoegen, dat begreep. Maar ik bedoelde alleen maar toevoegen aan material.
Yes.
Ik weet niet of ze dat bedoelen.
Okay. So the sticky air, what I use in sticky air is, well, it's basically a layer on top of there, a low viscous layer. And what I use as a boundary condition above there is that I just keep it open, so it's free to flow in and out sticky air material, basically. Yes, there's low density. Sir, that's the question. Yes. So it is a low density, low viscosity, or relatively low viscosity. It's still 10 to the 19th, which is, well, for air very high, but in comparison with the rest, it's okay. You can build realistic topography.
Great, and I don't see any more typing, so if anybody has any more questions, get them in now. I want to again thank both Cedric, Menno, and Anne for staying up late over in the Netherlands here to talk to us about their works. All very exciting stuff. We look forward to more exchanges. Hi, Anne. More exchanges out here in California in a few months, and of course your presentations at EGU. Thank you, everybody, and have a good afternoon, evening.